So hello and welcome to the first in our series of talks in which we'd like to consider the biblical account of creation. And in the light of modern science, we're going to be asking the question, is belief in the first few chapters of Genesis being proved unreasonable by modern science? Or can we take the vision that's given in Genesis of 6 days in creation in 6,000 years ago as a reasonable conclusion of the scientific evidence? So let's consider the two opposing arguments for a moment. What do you see here? Well, it's clearly a work of art, a painting. It includes natural elements of fields and trees and a river, and some man-made features of a building and a cart. And we know this to be the Hay Wain, painted by John Constable and finished in 1821. We know its origins because they're well documented. In this case, it'd be very hard to say the picture came into place by any other method than it was painted by an artist. So when we come to the natural world, we're confronted with a similar dilemma. We see the wonders of diversity. The world around us is full of complexity, the interactions of many different forms of life. And we can ask the same question. Is it the result of time and chance described by science, or was it created by a God as the account in the Bible? So these are our choices. Is the geological column a sensible conclusion, a response to the evidence we see beneath our feet? Or is faith, and some would say an old and out-of-date book, still tenable? We want in this series to look at the evidence so that you can decide which of the two is the most reasonable position for you to take. And we'll also consider if there's a middle way. Is it possible or reasonable to hold the middle ground, to accept that the world was created and that science explains how this was done? It's usually called theistic evolution. So that's a massive subject, and there's no way we'll be able to look at all the aspects of it, but we hope to open your minds to some of the possibilities in this series. To consider our subject, we'll split it down into various parts. Now, there'll be some overlap in the areas as we go, but it won't be really until the end when we consider everything that we'll be able to draw some conclusions. So to start with, we'd like to just make the statement that we really don't have the answer to all of the problems, although respectively we'll claim that neither does science. We'll try and be fair when we come to these problems, and we'll present the evidence so that you can come up to your own conclusion. Though clearly we hope that you'll agree with us that there is sufficient evidence to believe the biblical account of creation is credible. So our first consideration, the age of the earth. And we want to start here, not because that's the most compelling argument, nor frankly, I'm sorry, but neither is it the most interesting. It's a bit sciencey this evening. But because it's the crux of the problem. It's difficult to move forward without having first considered this. Now, the current position that science takes is there on the screen for you. That the universe is about 13.8 billion years old, that our Earth was formed little over 4.5 billion years ago, that life started with bacteria about 3.7 billion years ago, but it was during the Cambrian explosion for 540 million years ago that life really started as we would know it to be. And the alternative position, as we've said, that God created the world in 6 days, 6,000 years ago. So on the face of it, the Bible is not compatible with the evidence. How can we take the Bible account seriously in the light of these modern dates that science presents to us? So let's look at the scientific position so that we can understand it. Now, neither of these two men were the first to propose their theories with which their names have become synonymous, but perhaps their works, more than any other, has started the general ideas towards the accepted scientific position this taken today. Charles Lyell's book, The Principles of Geology, was one of 2 books that Charles Darwin took with him on his voyage on the Beagle. The other was the Bible, though he referred to the second very little. And it was the principles that Lyell laid down about the long periods of time that gave room for Darwin's theory of evolution as the origin of species. Both men started with an idea or hypothesis and looked for evidence to support that idea. Lyell was always an atheist, though Darwin was the son of a Methodist minister, though he soon rejected his Christian beliefs. So both men were looking for evidence to support the hypothesis that what we see around us is the result of natural processes. So how are these ages derived at? Well, science takes up a number of lines of inquiry, but perhaps the one we are most familiar with, and which is most often gives precise numbers, is radioactive dating. In brief, the science goes like this. The world is made up of lots of different elements, and some elements come in different types or flavours, and they're called isotopes. Now, the name of the element is given in straightforward text, and the number is the size of the nucleus of the element, and is called the isotope. So not all elements and isotopes are stable, but change with the passage of time. The starting position is called the parent, and the final position is called the daughter. And the ones that are used for radioactive dating are these. So carbon-14 becomes nitrogen-14, uranium-238, lead-206, uranium-235, which is the one they like for bombs, becomes lead-207, potassium becomes argon, rubidium, strontium, and samarium neodymium. So with the passage of time, one element or isotope becomes another. A parent becomes a daughter. And by taking samples from a rock or something else that we want to know the age of, and carrying out a detailed analysis of the elements that it contains, scientists can measure the amount of parent and daughter isotopes in a sample. And this is done with great accuracy. So how does that tell us the age of a sample? Well, the rate at which an isotope decays has been measured, and you may have heard the term half-life. This is the amount of time it takes for half of a parent element to decay into the daughter element. So in this example here, the blue becomes the yellow. And as you can see, after about 10 half-lives, there is very little of the parent isotope left. In fact, after about 14 to 16 half-lives, there is nothing measurable left at all. Now if we know the proportion of parent and daughter isotopes in a sample, then we know where our sample lies on a graph, a bit like this one. And if we know where it lies, we know how many half-lives have passed. And if we know how long a half-life is, we can determine how old a sample is. Well, that's how the theory goes. So these are the half-lives of the elements or isotopes that are commonly used in dating. Now you will have heard of carbon-14, I'm sure. It has a half-life of a little less than 6,000 years. This means in practice the oldest age we can reliably or accurately measure with carbon-14 is about 50 to 60,000 years old. And after about 1 million years, there is no measurable carbon-14 left in the sample. So the other elements or isotopes that we use have much longer half-lives. So they can be used to measure samples that are much older. And here we have those half-lives measured up to 106 billion years. Now we've known about radiation and the way elements and isotopes decay for a little over 100 years since the work of Marie Curie. And we've been measuring the half-lives of these isotopes for almost 85 years. So when we come up with an age of over 100 billion years, it requires a large amount of projection in these times. For we're measuring over a fairly short time and coming up with a very large answer. So we're anticipating that everything remains constant and that the radiation decay is a constant rate. But there are some other things we have to know about when we're making estimations of age from radioactive dating. And these are that we know the starting position of our sample. We also have to know that there's been no contamination during the time that the sample was in the ground. No parent or daughter isotopes were taken or added. And the rate of decay must be constant. That's half-life must always have been the same, and there's no external influences that might have increased it or reduced it. Now, these assumptions are known about by science and they're not ignored. There are workarounds that are used. So the isochron method is used to estimate the ages of a sample when we don't really know its starting position, the proportion of parent and daughter isotope as they were when the sample was brand new. We often find contamination within samples, and this is evidenced by when a sample is taken, several measurements are taken from the same piece. And we'd expect then to get several results. And though we scatter amongst those results, some will be wildly younger and some will be wildly older than hopefully most of them, which will be in the middle. So we could ignore very old ones or the very young ones. But we don't really know which is the contaminated part or not. And we might just be accepting the result that we want and rejecting the real one. The rate of decay, that is universally assumed to be constant. But as we've already said, it's only been measured for a relatively short period of time. But let's move forward and see what results are typically obtained. So what do we find when we apply this method to the geological column? Well, it's a fact that the rocks at the top return much younger ages to the rocks at the bottom. And this evidence appears to favour the scientific position, or that the Earth is very old. And that needs an explanation. But what do we find when we measure the age of rocks? Let's take another line of inquiry. Now you'll remember that different isotopes have different decay rates. So it's a bit like having 4 different clocks all ticking away independently of each other. But at the end, they should all read the same time. In that example, they all read just a bit after 10 o'clock. So if we took one sample and measured it by the different methods, we should reasonably get the same answer from all of them. Within a small proportion of error, we wouldn't be bang on, would they? So let's have a look at some examples. Now all these next examples are taken from the Grand Canyon. It's a good place to take samples from because there's lots of layers of rock exposed. So here a granite has been tested and the ages have been determined, and we can see that the oldest is about 1.3 times the youngest, or an error of about 30%. And that works out in this case as about 150 million years between the oldest and the youngest. Here's another one. This is from a basalt, a volcanic rock, again from the Grand Canyon. And this time the oldest is 1.6 times the youngest, or a 60% error, or 540 million years. And there's another one, another lava, but a different sort of lava. Now this time the oldest is 3 times the youngest. And that's quite a problem, isn't it, really? That's not what we were expecting. Now all of these figures that we've been looking at have been using that isochron method that I described earlier. So the starting position has been worked around. These are the best ages that we can determine for these. Okay, so let's have another look at another method. What happens when we date rocks that we know the age of? Now, Mount St Helens erupted in 1980 and a new lava dome formed in 1986, and you can just see the lump in the middle of that picture. So what happens when we date these rocks from that lava dome? And those are the samples that we get. The whole rock is 0.35 million years ago. But when we split the rock down into its different minerals, we get different results again, but those all should be the same age. In fact, the oldest is 70 million times the age that we know the rock to be. So that's quite a big problem. But it's not the only occasion. There are 4 more times here from around the world that exhibit the same problem. And really most of them always do. The oldest in that example there is 77 million times older than the known age. So that's a significant problem. Okay, let's have another look at a different way. Let's apply some logic to the dating. Diamonds, it's a good place to start. They're the hardest thing we know, so we can discount contamination. Nothing can get in or out of a diamond. So the Congolese diamonds have been dated up to 6 billion years old, but the Earth is only 4.6 billion years old, so the diamonds are older than the Earth. Now, conventional theory says diamonds are between 1 and 3 billion years old, that they formed whilst the Earth was cooling. But when we look at a diamond in a carbon-14 analysing machine, we find that carbon-14 exists. So that suggests that the diamonds must be less than 1 million years old. Well, that's a conundrum that we can't really make a lot of sense of, isn't it? Let's have another look at another logic example. So here we have a diagram on the one side that shows a section through the Grand Canyon again. And we can see right down at the bottom layers of rock at an angle. And then the sidewall of the canyon is made up of layers of rock parallel to the surface. But that's a mile high, that canyon. So that represents a serious amount of geological time. We have highlighted there 2 lava flows. One right at the bottom is clearly a lot older than the one that's flown down the side of the canyon. And the photograph shows that lava flow down the side of the canyon, all the way down to the river. So what happens when we date the ages of those 2 rocks? Now, we think the eruptions that flowed down the side happened as late as when the Native Americans reached the continent, which in geological time is only a few minutes ago. But by the strontium rudidium method, those lava flows are coming up with an age of 1.143 billion years. So when we date the lava flows right at the bottom, which should be much, much older, we get a date of 1.11 billion years. Now that's a little bit younger than the ones that have flowed down the top. Realistically, they're the same age because you can't see such a small difference with the dating methods used. But it's still a big problem, isn't it? So let's have a look at the summary so far. Now, there is no doubt that the measurements taken are taken extremely accurately, and they reflect the elements and the isotopes that are found in the samples incredibly closely. But, as we've seen, when we compare different dating methods for the same rock, the results don't compare well. And when we date rocks that we know the ages of, we get vastly older ages than we were expecting. And when we apply logic to the results, well, we can't make sense of the data that we get. So what can we say? Well, there seems to be a problem, I think, of interpretation of the data rather than the data itself. Now, there are many other ways to date the age of the Earth, or at least to estimate it. There are 48 there given, and they all give much younger ages. Now, these don't all necessarily give exact numbers, as radioactive dating does, but they do give maximum ages to which we could say that the world is. They set a limit. So let's have a look at just a few quickly that are easy to explain. Comets. Now, comets are assumed to have formed when the solar system was new, about 5 billion years ago. But we can observe comets as they pass the sun. The solar wind blows material from them. So it's difficult to think that comets can last any much more than 10,000 years or so, which is a big difference. What about the Earth's magnetic field? Now, the Earth's magnetic field is generated by the spinning iron core of the planet. That is slowing down as the planet cools and with friction, and so the magnetic field is also reducing. About half of its strength is lost every 1,400 years or so. Now, if you project that backwards, at about 10,000 years ago, the Earth's magnetic field would have been so strong as to be similar to that of a magnetic star, which is the strongest thing that we witness at all in our universe or could be imagined. So we have a maximum life of the magnetic field at about 10,000 years. Salt in the sea is one that's been talked about over many years. Oceans are assumed to be about 3 billion years ago. But again, assuming current rates of erosion and starting with fresh water, then the oldest we can reasonably guess that the oceans could be is about 62 million years. But again, that is the oldest that we could say that they could be. If we add a catastrophe or two, then they could be a lot younger. Dinosaurs are my favourite. So when we look at the fossil record, what do we get? Well, amber contains DNA from insects, and amber is assumed to be about 135 million years old. But if it contains DNA, how could that last? We really can't imagine that the DNA could be older than about 6,000 years. And dinosaur fossils, thought to be just 70 million years old or so, contain soft tissue. This is a relatively recent discovery. And again, we can't imagine that soft tissue could last any more than 10,000 years. And then when we date carbon-14 dating of fossils, we find that there is carbon-14 in fossils, so they can't be more than about 1 million years old. So what can we say? We haven't really determined the age of the Earth, I don't think, by the methods that are used. Rather, we have set maximum limits. So if we radioactive date rocks, we might say that the Earth is no older than 4.54 billion years old. But by other methods, we come up with much younger ages. See, Lyell and Darwin were looking for evidence that the world is a lot older. And if you want to draw that conclusion, you can find evidence to support it. But you do have to ignore a lot of other data. We are presented with dates from experimental data as if they are irrefutable facts. But we have looked at evidence this evening that would suggest that they're not as firm as we are led to believe they are. I don't believe in this presentation tonight that we've proved the biblical account is correct or that the world really is 6,000 years old. But we've chipped away at that foundation, that bedstone of scientific position that the world is a very old place. We've looked at methods that might suggest that those figures are only maximum figures and not actual figures. And this leads us to a position where we have to question that the world is the result of the natural forces that are carrying on all around us every day. And we'll be touching on these themes again as we go through these presentations and building up a picture. So this is our plan for the next few presentations. we've looked at this evening at the age of the Earth, and we've suggested that it might not be as old as science says. It's been a very physics and geology night tonight. Next time we're going to look at the complexity of life, and it's chemistry and biology that we'll be looking at. And then we're back to the rocks and physics in the record in the rocks and of the rocks in the third presentation. The origin and diversity of life is chemistry and biology, and the fourth one. And then a consideration of the evidence in the fifth one. Hopefully we'll be able to pull everything together and see what the conclusions are. Now, each time we'll be providing a reference list for those that want to check the data that I presented, or indeed that want to do a bit more of their own research. So I'll leave that screen up for a moment for you to have a look at. The reading list I can particularly recommend In 6 Days. The first one there, it's an account given by a number of scientists that have looked at the data, or professors and professionals in their field, and 50 of them have written a few pages on why they think the Earth isn't as old as we're being told it is. So we hope you found this interesting, and you'll join us again for more presentations.
The interesting thing then, just a question for you, is that there's many dating theories, just checking I've got this right, there's many dating theories, there's quite a lot of inconsistencies between them. So why is it then that people say that science is fact and treat the Bible as fiction?
Well, yes, a good question, Tim. I think, as we said, Lars and Darwin have started this off, anticipated that we're looking for old ages. And the radiocarbon dating is a very mathematical process, so we can add numbers up and come out with precise ages. So it's preferred by scientists because it gives us nice numbers that we can work with. But as we've said, there are lots of other methods that call that into question and doubt, and suggest that it's not as straightforward as we would think. I highlighted some of the problems of the starting condition, the contamination, and that radioactive decay is being constant, and those perhaps we'll come up again against them in later presentations. But it's evident that every one of those can realistically be called into question, and there are some problems with them that would suggest that they're not as accurate as we'd think.